Good morning all and welcoming to all of you. So previous class we were discussing on group theory. Says group theory. We are discussing on group theory, and in previous class we have discussed symmetry elements and symmetry operations. And on that class we have discussed that symmetry elements and symmetry operations are interrelated and they are used simultaneously. And next we have discussed all the symmetry elements, that says identity elements represented by E. Also we have discussed axis of symmetry represented by Cn. Also we discussed plane of symmetry, that is represented by sigma. So next we have one is improper axis of symmetries, improper axis of symmetry, and other one is center of symmetry. So these three we have discussed, this one. After this we have discussed, this we will discuss today. Okay, so today our class will be on improper axis of symmetry. Improper axis of symmetry. So we have already discussed that axis of symmetry and plane of symmetries, and we get that this axis of symmetry and plane of symmetries, and when these two symmetries elements, if you combine them, then we get the improper axis of symmetries. How we will look? Let's say improper axis of symmetry, if I define, then rotations, or I can say when a molecule if rotations followed by perpendicular reflections, if rotation followed by perpendicular reflections, if we get, or it's better to, we can say that rotations followed by perpendicular reflections if we get equivalent orientations of the molecules, then it is called, equivalent, it is called improper axis of symmetry. Improper axis of symmetry means that two operations we are applying here. One is rotations, that is Cn axis. This is here Cn axis, and perpendicular reflections, again you are applying sigma, means two symmetry elements you are applying Cn and sigma. After that, applying these two symmetry elements, if you get that equivalent orientations of the molecules, then that operation is called improper axis of symmetries. So this it is represented by Sn, and whenever you are writing this, but starts right from right to left. It means this is right, then right to left means here I will start and here I will end. Means operations will be done from right to left. Okay, from this is right, then right to left, the operations will be done. Let's say if I say that rotations followed by definitions, if you say the definitions which I have written above, that I say that rotations means Cn followed by perpendicular reflections, means rotations followed by perpendicular reflections, means this I am writing this is what in the word what I said, rotations followed by perpendicular reflections. So rotations followed by perpendicular reflections. Rotations means first I will write rotations, then only I will to do the perpendicular reflections. Similarly way, this also you can write this also, right? Also you can write reflections followed by perpendicular rotations. This one, what, how can you write? First reflections means sigma, after that perpendicular rotations means this one. So both the yes, we will get that Sn axis. Both the case Sn axis we will get. Okay. So now if we take the examples, let's take the examples. Let's say if I take about of that BF3 molecules, then I would take, let's say BF3 molecules. Let me write here B. This is F. Let's write 1, 2, and 3. So first, but either rotations or this is, let's say case 1, let's say this is case 2. So if I am doing here that here I am applying the case 1, then what I will do, first rotations. So I will do rotations. Here the sigma Cn is maximum times, this is principal axis. So here principal axis is C3. So first rotations, then I will do rotations. So this will go here, this will go here, this will go here. So this will becomes B F F F, then F1 will go here, F2 and F3 come here. So this is that. After that, what I have to do, rotations, after that reflections, then now perpendicular reflections. So now what I will do, perpendicular reflections I will apply. Means this is the planar molecules, means this in the wall, then if I apply that, let's say it's perpendicular to this, means this will come back, this will also go back, means this will look how, let me draw downs. So this will be B F F F, and since I am applying that perpendicular reflections, means this will not change, because in the above I am putting the one mirror. So sorry, this is F2, F1. So this front will become back and back will become front. This will go to back. Okay, so now this is perpendicular sigma. So now these to this, let's say this is 1, let's say this is 1, this is 2, and this is 3. So from here to here, that equivalent orientations according to definitions, what it says that if you do the rotations followed by reflections, after that if you get the equivalent orientations of the molecules, then SN axis is present. So here the C3 axis I applied, after that I get this one, and after that I again apply the sigma, after that I get this molecule. So here this in place of atoms, atom is there, although this is gone to back sides, but atom is there in this where the space, in which space atom was there, on that same space atom is there. So this is the equivalent orientations. Okay, here what things are present? So 1 and 3 are equivalent orientations, Similarly 1, this is 2, similarly 1 and 2 also equivalent orientations. So here 1 and 3 equivalent orientations means we know that C3 perpendicular sigma, that is equal to S3 axis, means here S3 axis is present. Okay, because S3 axis means that is rotations followed by reflections. After rotations followed by reflections, I am getting equivalent orientation, although this is going back sides, but in place of atoms, atom is there, then that is called equivalent orientation, that we already discussed in the past class. Okay, so here S3 axis is present, S3 axis is present. Similarly 1 and 2 are equivalent, so C3 axis also present. And in the other case, if I write this one, I will write in the corner. Okay, because I am drawing another picture here. So 1 and 3, 1 and 2 are equivalent structure. So 1 and 2 means C3 is present, C3, and 1 and 3, these are also equivalent, so S3 axis is present. Similarly, now if I apply another, this is the case 1 case, rotations followed by perpendicular reflections. This way also possible, that reflections followed by perpendicular rotations. So now if I apply that sigma, that is reflections, then what happened? That this will be B, F, F, F. So this I am applying the one in front of it, in the above I am putting the mirror, so it will be this, then it will not exchange, so this will same F1, this is F3, this is F. So this is just go to the back sides. Okay, that we already discussed. This will just go to back. Now I will apply what? Reflections followed by perpendicular rotations. So now if I apply to this perpendicular CN, so wherever that I will apply the CN axis. Okay, so here first I apply that perpendicular sigma, means the sigma I will apply. Now I am applying that CN, because it is not that I apply the CN, because CN axis means principal axis. Okay, so here first I will apply the perpendicular reflections. I will put the mirror in above of this molecule, so that will get back will go front and front will go back. Okay, so now I will apply CN, then what it will rotate, so it will become B. So the F1 will come here, F2 will go here, it will go here, and this is still in back. So you see that this one, let's say this is 2, this 3, let's say I will put this is 4, let's say I will put this is 5. So here that in place of f is there, it is not a backend, means in this space again, means this is f, here is one space, here is one space, and this is one space. So in this space f has came, here also like that, f space space space, in the space f1 f2 f3 space. So in which that we already discussed actually. So in space of f1, in place of f1, in the space where f1 is present, the same times f1, or that is, we are just for distinguish, we are putting that f1 and f3, although all f are same. So in place of f has came. So these are equivalent orientations. These are equivalent orientations. So that we already discussed what is the equivalent orientations. So 1 and, let's say 1 and B are equivalent orientations. It means S3 is axis, and 1 and 4 are also equivalent because in place of f is there. So this is also equivalent, means sigma is also present. Means in BF3 molecules, what you see that, so for BF3 molecules, S3 is present, let's say C3 is present, and sigma is present. That is perpendicular sigma, that is because to the principal axis, the perpendicular to the principal axis is horizontal plane, that is sigma h, that is also present, and S3 axis also present. Okay, so in this case we discuss that. So this is the case one case where that this also fine, we can do either this way, also we can do either this way. So this is the case one where I got the same equivalent structure. All, and if I do in the reverse also, I get the, this is the case 2 where I also get the same structure. Means F1 I rotate like this, here also I rotate. Okay. So here also we get the same structure. Let's say I will these and these are identical. It means that you can use either this way in this way. So both will give you the same results. Okay, so you can do either rotations followed by reflections, or reflections followed by rotations. The rotations followed by perpendicular reflections, or perpendicular reflections followed by rotations. So both will give you the same product, the same result. So both cases, anyone we can use it. Okay, and here what I observed that for BF3 molecules, C3 is present, sigma h is present, and S3 is present. Okay, so you understand that what do you mean by improper axis. So here both rotations and reflections both are combined, and they give the product that is S3 axis. Okay, next case, another examples we will do. Let's say ethane molecules. Let's talk about that staggered ethane molecules. Let's talk another examples. Let's discuss, that is staggered ethane molecules. Okay, so let's say this how it look. Carbon, let's say you can draw like this, right? Simply we draw like this, sorry, H H H H H, H. But for this group theory, if you draw like this, then it will be very difficult to find out that elements. So what we'll do, we will draw the structures. So in, let's say like this, and if the molecules is one is Y, straight Y, then other is inverted Y. Okay, and this one in Newman projection rule, what we will draw, that Newman projections we will do to understand this will makes the to identify the symmetry elements. So what we do the Newman projection. So one, this is the above, this point says above, we already, this is organic, we very familiar that this point represent front, so front side this, and that this one, this circle represent back side, this point represent front, and this circle represent back. So back sides I can write this, this, and this. So this is front side, let's say this atoms, and this is back side, sorry. So this is front sides, then what I do, front sides, and this is back side. So back side I will draw like this, and this. Okay, so this is the how to draw the Newman projection draw. Okay, so now let me draw one molecules, let's say ethane molecules. So this is the ethane molecules, this is actually what say these molecules I will draw in this form. After that I will convert into Newman projection, means this is Newman projection I do in this form. So but that front is in Y, straight Y, and back is inverted Y. Okay, so now what I do that here, if I apply, so this angle is here, H is there, hydrogens, let's say these are front H1, H2, and this is H3, these are the front H, and this is the back, this and this, and this is which is in the circle. So let's say that is H4, H5, and H6. Okay, and the angle between this one and this is 120 degree, because any molecules, this is actually, this form is this type of forms, and they have between their edge 120 degree. Now whenever I put in the one directions, then Newman projection rule, then what happened that this is the dihedral plane, because this bisecting these angles. So and this dihedral plane, this angle is 60 degree. Okay, because this is half of it. Okay, so now what happened that now if I apply, this is 60 degree means S6, that is 360 upon 60 means how much, S6 means C6. So if I rotate upon C6, then what I get, okay, here I am applying at C6, then what I will get that this H4 will means everybody will get change, means this will go here, and this will go here, and this will go here, this will go here, and this will go here. Okay, S6. So this the h1 will go here, see. So this which is that back sides y, that is inverted, that will become straight y, and this which was the straight y, that will become inverted y, because this is going here and this is going here. Okay, let's say it will become like this. Why? Because this h1 is go here, okay, h1 here, and this h1's go here, and h2 will go here, because h1 will go here, and this h2 is go here, and this s3 will go here. So this is going to s3, same case. And whatever the backside y means which is in the circles, so this s6 is going here and this is going here, means everyone are moving by 60 degree, right? So this h6 is going here, okay, h6, and h1 is go here, and this h4 is going here, and this h5 is coming here. It means if you look that, then the front one which was like straight y, that has become the inverted y, okay, after doing 60 degree rotations, because this h4 is go here, h2 go here, and h5 go here, and h3 go here, and h6 come here, h6 and h1 come here. Okay, so the y which was the front y, means this which is in the point side, that is the point, that is the front y. So that front y, that will become inverted y, and that back side y, means this gold represent the back side, this y was inverted, that become the inverted, that become the straight y. Okay, so you can look it. So now I apply c6, and for checking of s6, what I have to do, c6 into followed by perpendicular reflections. So I have to apply perpendicular reflections. So here, if I apply that perpendicular reflections, then I have to put one mirror in this point, so whatever the front, that will become back, and what will be the back, that will become front. Yes, so which is the front, this which y, that is the inverted y, sorry, that is straight y, which is in the circle, that will become front means in the point, means this is back side, because in the circle, so that will come to the front means I will represent by point, means I have to represent like this. Okay, and whatever is the in the point, that will go to the circle, because that is the back side representation, so that will go to like this, and the atom will not change. So h1 means h1 will be here, h1, h4, h2, h5, h3, and h6. Okay, so if you look at these two molecules, then this is this y, and this becomes what I'm discussing about of the front y, means front that I'm discussing about of that front carbon. Here front carbon is straight y. Now here the front carbon is like this, and here the front carbon is again like this. So if you what you know, that s6 means c6 followed by perpendicular reflections. So this y, straight y, and this is also straight y, means why I'm saying straight y, because this molecule is actually what, this is actually like this, that is actually like this. So whenever, if you rotate it, that C6, then what is happening, that this is going like this, and this is getting like this. Okay, and whenever again if I apply that sigma, then this is happening, that is again this is this direction. So to understand it, by rotations I draw like this. So you see that this is the same, this is y, straight y, this is back y, here also this is straight y, this is back y, and here this is back y, and this is front y. So you see that here in these molecules, whatever the atoms is there in this space, atoms is there, but here no atoms is there. Here no atoms was there, but atoms has come here. So this and this are non-equivalent, means in place of atoms, atom has not come. So whenever I did the S6 rotation, this is equal to this and this is equal to this. Because of the rotation simplified, I draw this in this form. Okay, so in place of atoms, atoms has not come. So these and these are not equivalent orientations. I mean, this means this. Actually, Newman projections I did to understand the rotations. So if I write this is 1, and if I write this is 2, and if I write this is 3, then it says this is 1, this is 2, and this is 3. So you see that 1 and 2, 1 and 2 are not equivalent orientations, not equivalent orientations, because in space that no, this means these are same. Okay, so 1 and 2 are not equivalent orientations. Similarly 1 and 3, 1 and 3, these are these atoms. So in place of atoms, atoms has come, in space of atom, atom has come, in space of atom, atom is there, in space of atom, atom is there. So 1 and 3 are equivalent orientations. It means what I say, that S6 after that sigma, then this is equal to S6. It means here it means S6 axis is present. So from here what I write, that since this is C6, so C6 is not present. Yes, because these are not equivalent orientations, so C6 is absent. So I write that S6 is absent, and sorry, not S6, this is C6. Okay, this is C6 is absent, but this and this and this and this and this means this comes after rotation followed by reflections, means this is S6. So S6 is present, S6 is present. So and other one also I can do that. So shall I erase it? I will erase it. Yes, I have to erase it because I will draw another plane. So now this how S6 we get, either this one or S6 also you get sigma, a perpendicular sigma followed by S6. So now I will apply S6 here. So either we can go this way, other way also you can do this. So other way I am doing, that is I will first apply sigma. So if I apply perpendicular sigma, then what happened, that whatever the inverted whatever the straight y, that will become front y. So this, the front carbon become inverted y, so this become like this. Okay, and whatever the backside y, means these circles, that will become front y. So whatever in the circle, that will become straight y. Okay, so the same atoms will say, whatever the atoms, that will remain as it is. So it will become same, just front become back, back become front. H4, this is H2, and this is H5, and this is H3, and this is H6, and this is H1. Okay, now I will apply sigma, sorry, no, I will apply now C3, sorry, C6, because C sigma followed by C6. Now apply C6. C6 means I will rotate everything by 160 degree. So what I get is that rotations I have to do see this H4, or I can say this H4 will go here, and this H4, whatever I did little bit, the molecules bit little bit bent, let's say this. Okay, so here I am applying the sigma molecules. If I have sigma molecules, then what, this front will become, this front carbon, that will go to back, means this straight y become back y, sorry, that is become back sides, and straight become inverted. Okay, and whatever that sorry, this, whatever the back, this straight, the straight y become inverted y. Okay, because the front will become back and back will become front. So this is H1, H2, H3, so this will go to back, and whatever the front, that will come to the, okay, so this circle, that will come to the front, so that will I do like this, that will come to the front, and whatever in the circle back, that will go to the circle front, that will go to the back, so like this. Okay, so the same atoms will stay at as it is, H4, H2, H5, H3, H6, and H1. Now if I apply here that S6, then it will just rotate, this will go here, this will go here, and this will go here. So just rotate it. If you rotate it, then this will go here, H4. If you go here, then H5 will go here. So I'm looking about of this one, which is in the front one, because this represent front point. So this front one will go here, and this will go here, and this will come here, because a 60 degree rotation. So this H5 will come here. Okay, so H5, let me do, so H5 will come here. Okay, and this H6 will go here, so H6 will go here, H6 will go here, and this 30 atoms, H4 will go here, so H4 will go here. Okay, this is the part of that front one I have done. Now I will do the back one. Back one, this will come here, S3 will come here, so here S3, and this will go here, come to the H2, and this S3 will go here. So if you look at if you look at the molecules of this is 1 and this is 2 and this is 3, so this is I write 4 and this is I write 5. So from B and 3 we will look that this is the straight Y, this is the straight Y. So here also you see that this is the straight Y, and here also we have the straight Y, means which is in the front atoms, that is in the straight Y. Here comes S1, so this is not S3, this is comes H1. Okay, so you see that this and this are equivalent, means you see all H1, H4, H2, H5, H3, H6 and H1. So either you will do by H6, after that rotations followed by reflections you do, or reflections followed by rotations we will do. We will get the same molecules, because you see that these molecules and these molecules are identical. Okay, this molecule are same. So either we will do that direction or we do this directions. And now the thing is that this is front carbon is straight Y, this is also straight Y. It means that these and these 1 and B are equivalent orientations. It means that I can write 1 and B are equivalent. Equivalent means S6 is present. S6 is present. S6 is present because sigma followed by rotations is H6. This is H6. S6 is present. But whether sigma is present or not, see, this is inverted, this is straight Y, and this become, this front carbons become back Y, means this is straight Y, this is inverted Y, means these are not equivalent orientations. Why this is not equivalent orientations? I already explained that this actually means that this is like this, this is like this, and this is this way. So here atoms is, here atom is there, here atom is not there, here atom is there, here atom is not there. So these and these are not equivalents. But you see that here front is like this and back is, sorry, back is like this. So here atoms is there, here also atoms is there, here atoms is there, here atom is there, here also atom is there, atom is there. So these and these are equivalents, but this and these are not equivalent. It means that 1 and 4 are non-equivalents. Non-equivalent means sigma is absent. So what is overall what we see that overall what we see that 1 and 2 are overall we see that S6 is absent and sorry, C6 is absent and sigma is absent, but H6 is present. It means both C6 and sigma absent. For what? This is for ethane molecules, staggered ethane molecules. Staggered ethane molecules. See that both C6 and sigma are absent, but S6 is present. Okay, this is the one important results. And another result is for ammonia molecules, what is it? For BF3 molecules, what you say is that C3 is present, sigma is present, and S3 is also present. C3 or sigma. Okay. So here both So if I combine it, then what I write that for tagged ethane and for BF3, here that C6 is absent. Here that C6 here principal axis or in C6, here C3 is present. Here sigma is absent. Here sigma is present. Here S6 is present. Here S3 is present. Means that for exist of S6, if that proper X is absent and sigma is absent, but still improper S6 is present. Here C3, that is the proper X is present, sigma is present, and also S3 is also present. Okay, so this that we will give that why this is, what is the conclusion, and what is the general formula we will discuss. Okay, so let's discuss more. After that we will conclude about it. So let's look now that Sn. So for n even, or n can be odd. So this n is the order. So if n is odd, then what will happen? So Sn and n equal to even, then the number of operations required to get the identity molecules each. Let's take about n is even. Let's take n can be let's say 4, 6, 8, 10. N can't be 2. Why? Because S2 is I operations. Okay, and for odd case n can't be 1 because 1 S1 is sigma. Okay, that we will discuss. So now, so n can be 4, 6, 8, and 10. Let's say for S6. If I talk about of that S6, then what it says that this can be written as S6. So we know that whenever Sn means sigma followed by Cn. So this I can write Cn. I can write this n equal to 6 into this one. And if I write that 1, then I have to write 1 and 1. Okay, now similarly S6 2, then I will write C6 2 into sigma 2. Okay, so note also that we already discussed that this n and this is equal to E if n equal to even, and this n equal to sigma n equal to odd. This already we have discussed. Okay, so now this is the one case, this is the second case. Another like S6 3, then this I can write C6 3 into sigma 3. Okay, and so this is even, so I can write, and if I cut it 1 3, then that is given C3 into this is E, that is going to be C3, and this one 1, this is 2, that is C2 into this odd means sigma. Okay, now for case if I write discuss S6 4, then this is C6 4 into sigma 4, that is equal to this is 3, so this is C3 2, and this is even, then E, that is going to be C3 2. Similarly if I discuss C6 5, then this is 5 and this is odd, so this is sigma. Okay, now let's discuss 6 6, then this is 6 6 6, so this is odd, so this is even, then this is e, so c6 6 into e, that is, this is equal to 1, so this is 1 1, that is equal to e, because we know cn n is e, n equal to odd or even. Okay, so this is going to becomes e. Okay, now if I proceed another, then is 6 7, and this is 6 7 into sigma 7, so this, what we know that a m n, then a, sorry, if m greater than n, then always m minus n. So here m is 7, that is greater than 6, so this will write c6, sorry, c6 7 minus 6 into sigma 7, that is going to give you that c6 1 into, this is odd, so this is sigma. But we see that this values we are getting here, this values and this value is same, so we will not repeat the same values. So if you proceed again, let's say c6 8, then this c6 8 into sigma 8, then this is going to give c6, that is equal to 2 into, that is going to give you e, that is going to c, that is c3 1, and you see that this value and this value, that is equal to 3, right? So these values and this value are same, so after this the value is repeating, so we will not take this value, so we will erase it, because same value will come, so we will not include the same value again and again. So to get that identity element, to get the same elements, how much you have to do? We have to do SNN. Okay, so from here what we conclude that for n equal to even, for n equal to even, what SNN after SNN we get identity elements, means after SNN we get identity, or we get the same values after, means after this we are getting the same values, right? So SNN we get the same values, so we will not proceed, means we will stop after getting S66. So if n equal to, if for n equal to even, then SN up to SNN we stop the stopped. Okay, and this is the one results we get. So if n equal to even, let's say this is S6 S8 S10, whatever the molecules, if the S8 then if it is S8, then we will proceed up to S1 S8 2, and that we have to proceed up to these steps. There we will stop it. Okay, like that. S7, then S, like that. If S10, then we'll go S10 1 dot S10 10. There we will stop. After that the same value will get repeated. This is the one observations we see. And second observations what we see is that if you observe it clear nicely, then what we see that this one I can write also C333. Why I'm writing? You see, here this is C3. One 3 I get here. Another C32 I get. Let's say this C31. Then this is C32, and this is C33. It means what we observe that in Sn axis, what there must be must be Cn by 2 axis. There must present C and 2 axis, means see this is this Cn1, C31, C32, C33, means we know that C3 axis means which is present C31 plus C32 plus C33. So these all axis present, means C3 axis is present. C3 axis present. Okay, so if C3 axis is present, so for this is for C6, we are talking about a S6, then C3 is present. If talk about a S12, then C6 will be present, like that. So if Sn axis n is even, then there must be n by 2 axis is also present in the molecules. But the vice versa, like, but the vice versa may or may not true. It means if C3 axis, if Cn by 2 axis is present, it means if C3 by Cn by 2 is present, then Sn may or may not present. That's the things. Okay, and another things what we observe that so from the above examples, this we did, but for staggered ethane, this C6 is present, C6 is absent. C6 absent, sigma is also absent, but S6 is present. From this S6 means here N is even, so for N equal to even, S6 is present, but sigma and proper axis is absent. So from here we say that this is all we are talking about of N equal to even. Okay, so we say that this is the very important points. If Sn is present, if sigma and Cn is present, then Sn must be present. This is fully safely we say that if sigma and Sn is present, then Sn must be present. Okay, so this is fully safely we can say this is always true. And another is if sigma and Cn is absent, then Sn may or may not present. So if these are absent, then Sn may or may not present. See here for staggered ethanes, these are absent, but this is present. Okay, so if this and this is absent, then also Sn may or may not be present. So if these both are absent, then also Sn may be present or may not be present. Okay, so this the 2 points. This is very important points. If both are present, then Sn must be present, but if this is also absent, then also Sn may be present or sometimes may not be present. So now let's discuss about of that. This is the 1 point. Okay, first clear these points. This is 1 point, this is 2 points. Another point is this is okay, so these 4 points we will be discussed. So Sn n equal to even. The first point is Sn it will stop up to Snn. Okay, second points, if Sn is present, then there must be C and 2x is present. X is present. Okay, but this is again one another point we will write. But if C and 2x is present, then Sn may or may not present. And 4 point is that if sigma and Cn present, then Sn must be present. This is 100%. But if what is right? If sigma and Cn absent, then Sn may or may not present. So for these points, these 5 points and these points, we only do by doing the operations only. There is no on the other way. Okay, so this we only do 3 and 5 only checked by doing operations, or by doing that experiment only. We understand, means we have to do operate this Snx. Snx means sigma followed by perpendicular reflections, sigma followed perpendicular reflections followed by rotations, or rotations followed by perpendicular reflections. So that Snx is, if we do on that only, we understand that whether Sn is present or not. But if the points like Sn is present, then must be Cn2 present. This is always true. And if Cn and sigma h is present, is true. I will write here. And if sigma and h is present, then there must be sigma is present. Okay, so from here I can point it out that suppose Cn exists, and if that sigma h is present, then we will get that Sn axis, because sigma Cn is present and sigma h is present. This is present. Okay, so this is present and this is present, then SNH must be present. This is the must. Okay, now if sigma h is absent, then what happened, that here we can do one thing, that see here that if Cn2 is axis is present, Cn by 2 axis is present, means we Cn by 2 this is present, then Sn may or may not present. So this is apparent at Cn, then because here C n upon 2 into, if I multiply by 2, then here S n into 2. So this cut, this C n is present, then 2, sorry, then S 2n. Okay, so this will be S 2n will be present or not. That means that you see that this is must be present. If Sn is present, then there must be Cn axis is present. So, but if Cn axis is present, then Sn may or may not be present. It means that if Cn is present, if sigma h is absent, first case is sigma h is absent, but we have that Cn axis. Cn axis means I will do it by like this. Cn, though this will become C2n. So if Cn is present, means that one, that Cn2, I do multiply by both side 2, then it's Cn2, then that will become S2n. So this S2n may be present. So we have to check may be present, but this will be not present, because sigma h is present, then this will be present. But if sigma h is absent, then from here that Cn2 Sn is present, then Cn must be present. But this is present and this is present or not, that is not sure. So what I say that if this is present and sigma h is absent, then S2n may be present. We have to check, this is highly possibility. Other case, if sigma h is absent, then Sn may be absent. Okay, so first case is that if sigma h is present, then Sn must be present. This is 100%. Okay, and if sigma h is absent, then S2n may or may not be present. Okay, this you will have to check. Means some 80-70% is that S2n may be present. Okay? But if sigma h is absent, other case Sn may be absent. Okay, these are the conditions we can look. Okay, so if sigma h is present, all that case Sn must be present, because Cn and sigma h is present. Cn and sigma h is present. Cn and sigma is present, Sn must be present. Okay, so this is must be present 100%. And sigma h is absent, because we say that Sn, it will be stopped and Sn present, then there must be Cn, but this axis Sn is present, then n by 2 axis must be present. Now that Cn is present and sigma h is absent, on that case S2n may be present. Okay, we will check this one. And other case Sn may be absent if sigma h is absent, but may also be present if sigma h is absent. S2n, probability is S2n, not Sn. We look about of S2n. Okay, so now let's look about of n equal to odd. Now n equal to odd, that means we will talk about of 3, 5, 7, 9, 11 like that, because S1 is going to give sigma. Okay, so we will not talk about of S1. Okay, so let's talk about of S5. So n equal to 5, S5, what it will look like? C5, because Sn is sigma upon sigma into Cn, so this is into sigma, so at the 1, then I'll write 1 S1. Okay, and case 2, if I look so this is even, then this into E, that is 5-2, and this is S53, then C53 into sigma 3, that is C53, and that is sigma, that is equal to this molecule as it remain, and this becomes C5 4 into this is 4, so this become E, that is going to become C5 4. And if I write the S5 so this is going to become E, and this is going to sigma because this is odd, so this is going to give even. Okay, let's check other like even if it is stopping or not. S5 6, then it is going C5 6 and C5 6, so this is going to be C5 6, this is going to be E. This is going to be C5 6, this is going to be E, and this value, so how can you write this one? On that way I'll discuss A, M, and if M greater than N, then M minus N we have to do. This is equal to C5 1. So this C5 1 we are getting? No, this is C5 sigma. C5 2 we are getting, but C5 1 we are not getting. Okay, so we have to proceed. Now repetition is done still now, so we have to repeat. C5 7, then this is C5 7 into sigma 7, that is C5 2 into sigma. So this is get repeated? I think no. Okay, this is there, but this is not there. This is 1, this is 2, not repeated. So we have to proceed again. S5 8, that's equal to C5 8 into 8, that is equal to 3 E, that is C5 3. This is also not repeated. Again I have to proceed. C5 9 into 9, then this is 5 4 into sigma. This is also not repeated. Then C5 10, C5 10, 10, that is equal to C5 5 into this is E. So this is also E. Okay, again I have to repeat it. C5 11 equal to C5 11 into this 11, this is equal to how much? 6 to E is equal to, so this value is repeated. Let's check whether the repetition is started or not. This is our value, is this value has come. Okay, this value is there or not? C5 6, C5 6, C5 6. This C5 6 again, this is much more greater than this is C5 6. Okay, C5 6 doing the same thing. This is C5 6 because 11 minus 5 6 into sigma odd, and this again greater than this, so I again write C5 1 into sigma. Okay, so now the value of mine is this one. So this value is there or not, I will check. Yes, C5 1 sigma, this also C5 1 sigma. So this value get repeated, means I will not have to use this. Let me try other whether this also repeated or not. C5 12, then this is going to C5 12 into 12, this is going to be C5 7, this is E, and this is C5 2. So C5 2 is there. Yes, C5 is 2 is there. So this value is get repeating, so we will not proceed because these are repeated. So from this what we observe is that unlike Sn where n equal to even, we stop up to Snn, we stopped we stop. We will not stop at SNN, but we proceed up to how much? That is SN to N. That is SN to N. This much we have to proceed. Where for N equal to odd. For N equal to odd, we have to proceed up to this much. Okay, this is the one points. And second points, what we observe that how many operations are there here. If you see that wherever the sigma is coming, here see sigma and S53 is there. It means this is S53 operations. So these operations we are getting, means improper access you are getting, but this is not improper access because this is proper access. C52 and E, which cancel out each. After that is this C52. This is proper access. So this will not conclude. This we will not include because this is proper access. So how many improper access you are getting? This one, another is this one. Wherever the proper access into sigma is there. So this two here also you are not getting because only Sn is there. Here only sigma is there. We will not include. Here also only proper access there. Here. So wherever the Cn and sigma is there, then only we are getting improper access. So this one also you have to take. Here only this. So we will not take. This is there. Okay, this one. So how many improper access we are getting? 1, 2, 3 and 4. It means another conclude we can say that number of operations for Sn is n minus 1 because here n is 5, Sn n is 5. The number of operations we get how much? 4. 1, 2, 3, 4. So here n is 5. A number of operations, that is improper access, we get how many? 4. So S minus 1, that is equal to 4. Okay, so number of operations for Sn equal to n minus 1, where n equal to odd. Okay, and what we will other things we understand that here n is odd, so sigma and for getting sorry, just a minute. Sorry, so for getting here what you see that is for getting this is for it. If sigma and Cn present, then there must be Sn axis present. Okay, this one point. Other points what we write here, that if sigma and Sn absent, both, okay, both absent, then sigma n must be absent. So here that clear cut, that if sigma and Cn absent, then Sn also absent. But for that n equal to even, if sigma and sigma is absent, then also Sn may or may not be present. But here that if sigma and sigma is absent, if sigma and Sn is absent, then Sn must be absent. Okay, for that odd, if sigma and Cn is absent, then also Sn may be present. But here if these are absent, then this is also absent. Okay, and also you can write, if Sn is present, then sigma and Cn corresponding to this Sn, okay, this Csn corresponding to this Sn, the Cn and sigma must be present. Okay, so these are the some points. So points is that number of operations, that is n minus 1 operation, and you have to proceed up to this much. And the important points is that if this and this are present, then Sn must be present. This is very important. And these are absent, and these are absent, then Sn must be absent. And this is present, then this is must be present. Okay, and for this case, if this is very important, if this is absent, then Sn may or may not be present, and this is only carried out by doing the operations only. And this is present, then Sn must be present. Okay, these things we have to look these points, and you have to do up to Sn, and then the C and 2 axis must be present if Sn is present. And if this is present, this may or may not be present. And if these both are present, then Sn must be present. And these are absent, then also Sn may or may not be present. But for the case of odd, n equal to odd, if these are absent, then Sn also be absent. And this is present, then this is also present. This is present, then this is present. This is the same point, vice versa points. Okay. So this is all about of that Sn axis, and I think it is fine to discuss up to this, and we will proceed the examples in next class. So next symmetry elements we will discuss, that is next one we will discuss, that is center of symmetry. So 6.1. So we will actually discussing about, so this one we have discussed. Now we will discuss center of symmetry. Okay, 6.1 is center of, so this symmetry is very easy to understand. 3.6.1 is center of symmetry. Center of symmetry. So for this case, what we say that it is special kind of symmetry elements which inverted all the coordinates of the molecules, coordinate atoms of the molecules, let's search. Okay, past. It is represented by I. Okay, so if you take examples like A, B, A molecules, like if I say that CO2 molecules, so CO. So here from this center, if you go here, same atom should be present. If you go here oxygen, here you go oxygen, means here I is present. Similarly, if I search H2, say H. So these points, any imaginary points, if I proceed that both sides, then hydrogen, here also hydrogen, here space, here also space, means I is present. Means both from this point, any point if I go, then I should get the same things, then I is present. Similarly, let's search. If I talk about water molecules, so from these points, if I go here, nothing is there. Here if I no go, nothing. Here if I go, nothing there. Here if I go, hydrogen is there, means I is absent. Means from the point, if you go any direction, you get the same things, then I is present. Okay. Like if we discuss of dichloroethylene, two types, let's search. So if I take about of Cl, I will take out H, and if I talk about of Cl, if I talk about H, this is transform, another is talk about of Cl, if I talk about of H, and this is, let's say, cis. Then if I say these points, from these points if I proceed, then I am getting Cl. If I process Cl, if I process Cl, this means I is present. Here from this point if I proceed Cl, but if I proceeding, hydrogen is there, means I is absent. Okay, so this is very easy to identify that one point if you proceed any directions, you get the same atoms, then I is present. Okay, after discussing this, we will discuss that two physical properties that are very important. Two physical properties of the molecules. We'll discuss. One is dipole moment, and third is optical activity. So if I discuss about of the dipole moments, then what I says that or we may proceed these things in the next class. So today up to this, thank you.